water, dihydrogen monoxide, H2O, DHMO, makes up about 70% of our bodies. It covers about 71% of the Earth's surface. It's also one of the most dangerous chemicals in the chemistry lab. Did you know this humble molecule breaks just about every rule in the chemistry book? So today, I'm diving, pun intended, deep into the bizarre world of water and why it stays liquid when it shouldn't, how it defies expectations, and why it's the secret behind life itself. So stick around for some cool demonstrations, as well as a discussion of the unique properties of water that make it necessary for life itself to exist. So let's start off by looking at some of the neighbors of some of the elements in period 2 of the periodic table. Specifically, I'm looking at the hydrides of the period 2 elements: boron, carbon, nitrogen, oxygen, and fluorine. The hydrides are boron trihydride, methane, ammonia, water, and hydrogen fluoride. Let's look at some of these properties in this table. Notice anything strange here? Water has way higher melting and boiling points than its neighbors, any of the other elements. Why is that? That's just weird. That's because water forms hydrogen bonds. These are very strong interactions between the slightly positive hydrogen of one molecule and the slightly negative oxygen of the other. Water also has a bent shape, 1 of 4.3 degrees. It's not linear. This is because the lone pairs on the oxygen move the bonds between the hydrogens the OH bonds a little bit further away. This makes water a very polar molecule. It gives it a dipole moment, kind of like a tiny little magnet, right? So if we take ice cubes and we put them in a beaker of water, notice one thing: the ice cubes float on the surface of the liquid water below, right? And why is that? That's because solid ice is less dense than liquid water due to the regularly ordered hexagonal lattice of hydrogen bonds in the crystalline ice structure. In liquid water, each molecule forms approximately 2 to 3 hydrogen bonds and constantly reshuffles. It's about 2.3 hydrogen bonds on average. Even at room temperature, that's absolute chaos. There's a lot of disorder. Bonds last just about 10 picoseconds, and that's only about 1/10 trillionth of a second. And that compares to about 10 microseconds for the length of a hydrogen bond in ice. Water also has a relatively high dielectric constant, and that's the relative permittivity. That's the measure of the ability of a substance to insulate an electric charge. The higher the dielectric constant, the more insulating the material is. For a vacuum, that is 1. For water, it's 78. That makes water an incredible solvent for ions such as sodium chloride. And water is also an excellent conductor of electricity, right? So let's take a look at that. And if I let's just take this setup here. I'm just going to take a little bit of water, like so. Oops. Let's get a little bit of H2O. I'm going to immerse that water between 2 electrodes. That water should conduct an electric charge, or maybe not. Maybe this thing's not working. Oh wait, I forgot something. I forgot the electrolyte, right? We need to add a little bit of electrolyte. That's our salt. That's the sodium chloride. that enables the water to conduct electricity, turning the light on, right? So pure water does not conduct electricity, but water with ions or electrolytes do conduct electricity, right? And so that's also a unique property of water itself. So water's polar nature also means that nonpolar substances such as oil will not dissolve in water, while polar charged particles such as the sodium chloride will dissolve in water. So let's take a look at putting oil. And put a little bit of oil here, and we need a little bit of water. Let's just take some pure water here, put it in. Now, if I mix these two together, just kind of shake these up. Now this looks relatively different from the other mixture. Now, first of all, it's going to settle, and ultimately when this settles, if you notice, the oil is less dense than water, just like ice, and the water is on the bottom layer. As it's settling, what's happening? The water is forming a water layer on the bottom, and the oil is a separate layer. Oil and water don't mix, right? If I shake it up, it'll appear to mix, but it's not forming a homogeneous mixture, and it's not a solution, right? So this is actually really important to life. This property of water, oil and water not mixing, is a major property of what makes membranes form in liquid water, because remember, the human body is 70% water. And so if we take oil and put it in an aqueous solution, the membrane will, the hydrophobic parts of the membrane will aggregate together to form a separate bilayer, and that's what makes life possible, because now it can form membranes around stuff. And so that's a very important property of water, the ability. So if you ever wondered how water moves into and out of cells, right? This is basically the process of diffusion. And this also makes osmosis possible, right? And so a 1 molar solution of water with a solute will generate an osmotic pressure of 22.4 atmospheres. That's about the same pressure as being 738 feet underneath the ocean underwater, right? So that's also a unique property as well. Okay, so this experiment here, this is a classic eggshell dissolving in acetic acid experiment with my acetic acid. And so what's going to happen here is the eggshell is mainly made of calcium carbonate, CaCO3, and the acetic acid will, over time, usually takes about a day or so, maybe half a day, we'll just see how long that goes. It's going to break down that calcium carbonate shell, leaving, you're going to see some CO2. Of course, it'll start bubbling. Well, probably won't see the CO2, but it'll bubble away, and then the eggshell will dissolve. It's going to leave a thin membrane behind. And so, of course, that membrane will be fairly flexible, and we'll actually be able to see inside the shell. So I'm going to start off, I'm going to put this inside of a beaker, very carefully, of course. And then we will take some of our acetic acid, and we will pour this. This is just regular vinegar, and just kind of make sure it's all dissolved. It's all underwater, right? There we go. So we want it all to be submerged. And actually, if I look at it, I can already see small bubbles in the egg, right? And if you kind of look at the egg very carefully, you can see the bubbles. It's already starting to bubble away, and that's the CO2 starting to form. Of course, the eggshell by comparison, is fairly thick. So it's going to take a little while to dissolve the egg. Let's see if we can see the bubbles inside there. Maybe click on the other side. There we go. So we're going to let that sit. We're going to let this sit overnight, and then tomorrow we can take it out. Then we can have a little bit of fun with it. We can actually put it in water, and there's enough osmotic balance from some of the dissolved ions inside the egg that it should change the shape of the egg, and it should cause the egg to decrease. So we'll let this sit for a while, and we'll come back tomorrow. We'll come back later. So let's take a look at our egg. And so this has been sitting in. It's actually been sitting in for about 2 days in vinegar. And so the eggshell should be mostly dissolved. I'm just going to kind of clean this off in the water a little bit. This is just water. So I'm just trying to get the vinegar mostly out of here. And so the eggshell is now pretty much dissolved. It's actually, kind of look at it, look at that. There's no shell, it's just a membrane, right? So I can put this into pure water, just kind of get the vinegar off of it, get it a little bit cleaner. We now have a perfect egg, and it's nice and it's flexible now, right? So if we kind of look at that, we've got a nice flexible egg. Now if I put this in water, there are, and if I let this sit in the water, there's also ions and other things inside the water. So if I let this sit, now the membrane will let water travel through the membrane, but the ions will not because they're charged, right? So if I let this sit over time in pure water, then we're going to see the process of osmosis take place, and water should travel through the membrane, altering the size of the egg. And so that's the case with the egg, because then we're going to see the diffusion trying to equalize the concentration of the solute inside the egg, right? Okay, so now let's weigh our egg, and I'm going to first start off by drying this egg with no shell. Make sure it's kind of nice and dry. I don't want to burst the membrane because then we'll have a mess, right? So we'll just do that. All right. So if I then come over here to a scale, now the first thing I need to do, I'm going to tear this. So we tear that, and then we can put this into our scale. Let's see. So this egg is 84.67 grams, right? Now, if I then take this egg that weighs 84.67 grams, and we're going to put this into water and let it sit. So I'm going to let this sit overnight, and what's going to happen is the process of osmosis, the water is more or less pure, and then there's more ions inside the water, so we have a higher concentration inside the egg than in the water. And so the process of osmosis, the water will travel across the membrane of the egg and in order to reduce the concentration of solutes. So the egg should gain a greater mass after sitting over time. So it should be higher in mass because water is going to be entering the egg after it's sitting for a while. All right, so my egg has been sitting in water overnight. Hopefully osmosis has been going through the membrane, so there's higher salt concentration inside the egg. So that should cause water to go from the water solution it's sitting in into the egg. So let's take the egg out of water and dry it off. Make sure we don't have too much water on the outside of the egg, because hopefully all the water is staying inside the egg. Now what's kind of cool is it's nice and bouncy. It's like a bouncy ball. Now what I'm going to do, take my container and make sure my container is taired. We'll tear the container and then take the egg and put it inside the container. And now my egg is 86.80 grams, right? So the egg has went up from 84.67 to 86.80 grams. And so it has gained water through the membrane as water has, by osmosis, has seeped into the egg, right? So we've actually gained, that's osmosis in action. Now, is water an acid or a base? Let's think about that. It's actually both. It's both an acid and a base. The acid form of water is called the hydronium ion, that's H3O+. The base form, if it loses one proton, that becomes H2O. Water itself can also donate a proton. When that happens, it's converted to the base form, the hydronium ion. All three of these are present in liquid water at room temperature at a given time. We see that, and it's established in a very rapid equilibrium, right? This equilibrium is the foundation of the pH scale. That scale was developed by Søren Sørensen of Carlsberg Brewery back in the early 20th century. And what he was doing, he was measuring hydrogen ion concentration, and ultimately his goal was to brew a better beer. So the Carlsberg Brewery, they literally invented the pH scale, studying water and how that's heavily used all over science and all over chemistry. pH literally means the negative log of the hydrogen ion concentration. So a pH of 5.5 has a hydrogen ion concentration equal to 3.16 times 10 to the negative 6 molar of hydrogen ions. So that's where, and here's where we tie it all together with the Henderson-Hasselbalch equation. That is pH equals pKa plus the log of A minus over HA. A minus being the base, HA being the acid. So this equation correlates the pH of the solution with the concentration of acid and base. If we look at a titration curve showing the increasing concentration of base on the x-axis compared to the pH on the y-axis, this curve shows a rapid increase in pH as protons are initially transferred from acid to base. That is followed by a gradual increase, a horizontal curve, in the pH as acid and base concentrations are close to each other and equal. We then continue to remove protons, and we get a more rapid change in pH as we approach the endpoint on our titration curve. And this equation helps buffer systems in your body maintain pH stability even in the face of complete metabolic chaos. So water defies all the expectations. It bends the rules of chemistry. And these unusual properties ultimately make life possible. It's not just a molecule, it's a miracle. Thanks for watching. I hope you learned something new today. Go ahead and hit the like button down below. Hit the subscribe button if you're interested in these. You want more mind-bending science. And be sure to hit the little bell icon so you're notified when we post new content here. And drop me a comment below about your experiences with water, your favorite water fact, unusual fact, anything like that. And I'm always interested. I always try and read these comments and see what students and others are posting. So I find that very interesting. So thank you again. And in the meantime, I'll go ahead and have another glass of water.